A rectangle is bounded between the x-axis and the semicircle y equals the square root of 25 minus x squared, or the top half of the circle x squared plus y squared equals 25. Well, what we want to do is find the length and width of the rectangle that will maximize its area. All right, so first let's see what we're working with here. We have the x-axis and we have the y-axis, and let's graph y equals 25 minus x squared. So it goes from -5 to +5 and up to 5 on the y-axis, and here's the semicircle, or the top half of x squared plus y squared equals 25. And inside that semicircle we have a rectangle. And if we look at the area of this rectangle, this is what we want to maximize. So we want to find the length and the width of this rectangle to maximize its area. And so let's look at this rectangle. What is the length and the width? Well, if this point right here is xy, then the height of the rectangle is y, and x accounts for half the base. So it looks like the base of the rectangle is 2x. And so our equation for area is a equals 2xy. And so this is called the primary equation. Now the problem with this, we can't work with this because we can't take the derivative of this because there's too many variables. There's 3 variables here. And so when we want to maximize something, if we want to maximize the area, well, maximums and minimums, or extreme values, could only occur at critical values. And we determine critical values by determining where the derivative is equal to 0 or where the derivative is undefined. So we need to take the derivative, which means we have to eliminate one of these variables. Which is fine because we're given this, that y is equal to 25 minus, or the square root of 25 minus x squared. 25 minus x squared. So we could replace this y with the square root of 25 minus x squared. So 2x, which is the base, times the square root of 25 minus x squared. Or I don't like using the square root sign, so let's say 2x times 25 minus x squared to the 1/2 power. So this is called the secondary equation. This is the one we're going to work with. It's what we get when we eliminate all but one of the independent variables. So we have a and we have x. And so now, since we need the critical values to determine where the maximum is, we need to take the derivative of this. All right, so now let's work with the derivative. dA dx, or the derivative of a with respect to x. Well, we have the product of two things here, so we need the product rule. And in the product rule, we're definitely going to be using the chain rule here. All right, so let's see if we could go through the derivative. The derivative, according to the product rule, says we'll take the first factor, which is the 2x, times the derivative of the second. And the derivative of the second is, according to the chain rule, well, the power comes out front, drops by 1, inside stays the same, times the derivative of the inside, the derivative of 25 is 0, and the derivative of the negative x squared is a minus 2x. So that's the first times the derivative of the second, plus the derivative of the first, derivative of 2x is 2, times the second, which is the 25 minus x squared to the 1/2 power. So we have to set this equal to 0 and solve. So let's clean this up a little bit first. It looks like this 2 and this 1/2 will cancel. So that first term, well, we have an x and a minus 2x, so that's minus 2 x squared, and we could bring that negative exponent to the bottom. 25 minus x squared to the 1/2. All right, so that's the first term in the derivative, and the second we have the 25 minus x squared to the 1/2. All right, so let's combine these terms by getting a common denominator. So let's take this second term and multiply it by 25 minus x squared to the 1/2 over 25 minus x squared to the 1/2. So that will give us a common denominator. (25 minus x squared to the 1/2. And let's see, on top we've got a minus 2x squared from the first term. And here, 25 minus x squared to the 1/2 times itself. Well, we have a 2 out front, and that will be just 25 minus x squared to the first power. And if we combine like terms, 2 times 25 is 50, and the 2 times the negative x squared is a negative 2x squared. So it looks like the derivative of a with respect to x is equal to 50 minus 4x squared divided by 25 minus x squared to the 1/2 power. All right, so that's our derivative. So we take our secondary equation, we find the derivative of the secondary equation, and we use that to find the critical values or the potential places where the function could have a maximum or minimum value. So we're going to find the critical values now. And critical values are where the derivative is equal to 0 or undefined. So that means when is 50 minus 4x squared equal to 0, or when is the square root of, or 25 minus x squared to the 1/2 equal to 0. So when's the top equal to 0? When's the bottom equal to 0? All right, so we're solving 4x squared equals 50, or x squared equals 25 over 2, or x is equal to, well, normally there'd be a plus or minus, but since we're talking about length, I'm just going to look at the positive value because length has to be positive. So 5 over the square root of 2, or 5 root 2 over 2. So this is a critical value. And then over here on the right, 25 minus x squared equal to 0. Well, that's happening when x is equal to 5. 25 minus 5 squared, or 25 minus 25, is 0. Now let's just, well, first of all, we know 5 is not the answer. Because if I go back up here, if you let x equal 5, then that's your point. Which means the base of the rectangle is 10 and the height is 0. So if x is equal to 5, we know that's out because it'll give you an area of 0. And so let's just make sure that the 5 root 2 is actually a maximum. So let's apply the first derivative test. Okay, so our derivative, let's see, go up a little bit more. Our derivative is 50 minus 4x squared divided by 25 minus x squared to the 1/2 power. So let's plug in some test values. So something a little smaller than 5 root 2 over 2. Well, this is about 3.5. Not exactly, but this is about 3.5. So let's plug in a 3 and a 4 into the derivative. Well, if we plug in a 3 to our derivative, 3 times 3 is 9, 9 times 4 is 36, and 50 minus 36 is positive. So you could pause the video and just verify this, but if we plug in a 3 to the, if we plug in a 3 into the derivative, you'll see we get a positive number. And so to the left, and actually not all the way to the left because maybe these arrows are misleading. So we're only going from -5 to 5. That's the domain of the derivative. But if we plug in 3, we get a positive number. And if we plug in 4, so remember these numbers, we're plugging them into the derivative. And if we plug in 4, that would be 50 minus 64 on top, which will give you a negative number. So the derivative is, negative to the right. So that means the function is increasing to the left of this critical value and then decreasing after. So we have a maximum value that occurs at x equals 5 root 2 over 2. All right, so going back to our, I'll copy it down at the bottom, but going back to our primary equation, we're maximizing the area, so we need the x value and the y value. So the x value is 5 root 2 over 2. And if we plug that in to our original function for area, if we plug that in for y, so 25, or the square root of 25 minus this value squared, we will get, well, let's work it out. 25 minus 5 root 2 over 2 square root, which is the square root, that's squared, the square root of 25 minus, well, that's 25 times 2 is 50. So that's 50 over 2 squared, which is 4, which is the square root of 50 over 4, which is equal to 5 root 2 over 2. Now be careful, this is not our final answer because we're not looking for the x and the y values. We're looking for the base and the height. So let me go back here, or length and width. So what length and what width? And remember the base and the height, whatever you want to call it. So the height of the rectangle is y, which we have, and the base of it, which we'll call the length. So let's say for our final answer, the length, which is equal to 2x. And so x is 5 root 2 over 2, so the length should be 5 root 2, and the width should be also, which is the y value, should be 5 root 2 over 2. All right. And that does it for the dimensions of the rectangle inscribed in the semicircle. That should maximize the area. All right, hope this was helpful.